ever stop to think about the actual ground beneath our feet? It's uh, it's way more than just dirt, isn't it? It really sets the stage for what can grow, what can
Yeah,
thrive.
it absolutely does.
So today we'll dig into a specific type, calcareous soils. We're basing this on some excerpts from chapter 6, really trying to unearth what makes these soils tick.
Exactly. And our mission really is to get a clear picture what defines them, where do we find them. And it's worth pointing out, India has a huge amount, something like 229 million hectares. That's nearly 70% of the country.
Wow, that's massive.
It really is. Uttar Pradesh, Bihar, they alone have over 1.3 million hectares each. So understanding these soils is vital there. We'll also look at the challenges they bring for farming and, importantly, how we can manage them.
Right. So by the end, you listening should have a really solid grasp of a soil type that's, well, pretty critical globally.
That's the plan.
Okay, let's start with the basics then. What actually defines a calcareous soil? What are the absolute essentials we need to know?
Well, the number one thing, as the source highlights, is a high amount of free calcium carbonate, KCO3. That's the dominant feature influencing how the land gets used, especially for agriculture.
Free calcium carbonate. Got it.
And these soils typically come from parent material already rich in KCO3. Plus, they usually have what's called a calcic horizon.
The calcic horizon.
Yeah, it's basically a layer deeper down in the soil where calcium carbonate has built up over time. And, in the big global classification system, the World Reference Base, they call these calcisols.
Calcisols. Okay, so high calcium carbonate, often a specific layer of it. Makes sense. Now, how do these landscapes actually form? What's the origin story here?
Formation. That's largely down to climate. Think arid and semi-arid regions.
Dry places.
Exactly. Low rainfall means there's not much water washing through the soil, right? So leaching is limited. This allows that secondary calcium carbonate to form and stick around.
Okay, so unlike places with lots of rain where it might get washed away deeper or dispersed,
Precisely. In high rainfall areas, the KCO3 tends to get flushed out of the upper layers, but in these drier zones, it accumulates. You also see it building up in the subsurface layers of certain soils, like medium deep and deep black clay soils.
accumulating. Does that cause problems?
It certainly can. If that KCO3 gets really concentrated, it can form these hard, almost cement-like layers. They're called caliche.
Kalish. Sounds
Oh,
tough.
oh, it is. It can be a real barrier for plant roots trying to grow downwards and for water trying to soak in. Really impermeable stuff.
Okay, so climate's key.
Hmm.
Any other ways they form?
Yeah, there's another interesting process. Sometimes, especially if there's irrigation and a shallow water table, salts can actually rise up through the soil with the water.
Like water wicking upward.
Exactly, through capillary action. When that water evaporates near the surface, it leaves the salts behind, and if calcium carbonate is dissolved in that water, it precipitates out right there near the top of that capillary fringe.
Huh. So irrigation can actually contribute to it sometimes.
It can intensify the process, yeah. So you've got the parent rock, the dry climate, sometimes these water table effects, and you typically find these soils on fairly level to hilly land, often with specific drought-tolerant plants like xerophytic shrubs and grasses that only pop up when it rains.
Right. Okay, that gives us a good picture of the how and where. Let's pivot to the challenges. What makes farming on these soils so, well, difficult?
This is where it gets really critical for agriculture. You'd think calcium is good for plants, and it is, it's essential, but too much free calcium carbonate creates a whole set of issues.
Okay, I'm like what?
First off, the soil reaction, it's alkaline. The pH is generally above 7.0. And importantly, these soils have a high buffering capacity.
Buffering capacity.
Yeah.
Meaning it's hard to change that pH.
Exactly. It strongly resists changes in pH. And the soil chemistry is dominated by calcium and magnesium carbonates, mostly that free KCO3 we mentioned.
And that high pH that has knock-on effects for plants, right? What are the big ones?
Huge effects. This is crucial. That high pH basically locks up essential nutrients. Even if things like nitrogen, phosphorus, potassium, sulfur, iron, zinc, boron are in the soil, the plants can't easily access them.
So the pantry's full, but the door's locked.
That's a great analogy, yes. And this nutrient lockout is probably the single biggest constraint on productivity in these soils.
Frustrating for farmers, I bet. Are there visible signs? Things you'd actually see on the plants?
Definitely. A classic one is Lyme-induced iron chlorosis.
Chlorosis, yellowing leaves.
Yes, exactly. The high KCO3 interferes with the plant's ability to take up iron, so the leaves turn yellow, particularly the newer ones. This can also really hit seed germination rates hard.
Okay, yellow leaves, poor germination. What else?
Well, Beyond the nutrient side, there are physical issues too. These soils often don't hold water very well. Their water holding capacity can be quite low.
Right, you mentioned the caliche layer earlier, too. That must make it worse.
It does. That hardpan layer, whether it's full-blown caliche or just a strongly cemented layer, restricts water movement and root growth. So less water retention and roots struggle to even reach the water that is there.
That sounds like a really tough combination for plants. Double trouble.
It really is. And it's complex because, calcium and magnesium can actually help soil structure initially. They cause flocculation, where soil particles clump together, improving aggregate stability.
Oh, so that part's good.
It can be good for structure deeper down, but paradoxically, it can also contribute to surface crusting. The soil surface can bake hard, like a crust.
Ah, so good structure below, but a barrier on top.
Yeah, and potentially that hard layer underneath, too.
Yeah.
So you end up hindering really vital things like aeration, getting air into the soil, water infiltration, like we said, and even just the physical emergence of seedlings pushing through that crust. It's a bit of a double-edged sword.
Definitely sounds like it.
And add to that, the drier conditions often found with these soils mean less activity from beneficial microbes in the rhizosphere, that crucial zone right around the plant roots.
Right, the soil life suffers too.
Mm-hmm. And, as if that weren't enough, these soils are typically low in organic matter and available nitrogen, which just compounds all the fertility problems.
Wow, it really is a long list of obstacles.
Mhm.
You mentioned phosphorus getting locked up specifically. What's the chemistry behind that?
Yeah, it's quite specific. At that high pH, the phosphate ions, which plants need, react very readily with the abundant calcium ions.
They kind of stick together.
They do. They form insoluble calcium phosphates, often minerals like apatite. This effectively takes the phosphorus out of the game, makes it unavailable for plants to absorb even if you add phosphate fertilizer.
So adding more phosphorus doesn't always help if the chemistry's wrong.
It can be inefficient, yes. And it's not just phosphorus. As we touched on, micronutrients like zinc and iron are also much less available at high pH, which ties directly back to that iron chlorosis, the yellowing leaves.
Okay. A challenging environment, no doubt. So let's move to solutions. What can actually be done? How do you manage these soils to make them productive?
Right, management. Given that these soils are often in low rainfall areas, the first most fundamental step is usually irrigation. You simply need to provide water.
Makes sense. Water is life.
Absolutely key. Then, thinking physically, you remember that hard caliche or cemented layer?
Yeah, the tough layer.
Well, physically breaking it up can make a huge difference. Using something like a chisel plow or subsoiler to shatter that layer improves permeability dramatically. Water can get in, roots can get down. It really aids reclamation.
So brute force can help break down that barrier. What about improving the soil itself, its fertility?
That's vital too. Adding organic matter is crucial. Things like farmyard manure, compost, or green manuring, growing a crop and plowing it in, they all help build up the soil.
How does organic matter help specifically here?
It does several things. It improves water retention. It can slowly release nutrients. It provides food for those beneficial soil microbes. And it can slightly buffer the pH effects right near the roots. It just improves overall soil health.
Okay, organic matter is key. Are there chemical approaches too?
Yes, definitely. You can use acid-forming amendments, things like elemental sulfur or pyrites or even ferrous sulfate.
Acid forming. So they counteract the alkalinity.
That's the idea. When they break down in the soil, they create acidity, which helps to dissolve some of that excess calcium carbonate locally, maybe lowering the pH just enough around the roots to free up some nutrients. Using acidic or acid-forming fertilizers can have a similar beneficial effect in the root zone.
That makes logical sense. Fight alkaline with acid, essentially. What about the specific micronutrient problems like the iron and zinc?
Good question. Since getting them through the soil is tough, a really effective strategy is foliar application.
Foliar, spraying on the leaves.
Exactly. You dissolve zinc or iron compounds in water and spray it directly onto the plant's leaves. The plant can absorb it directly, bypassing the soil chemistry issues altogether. It's a direct hit for those immediate deficiencies.
A way to shortcut the problem.
Clever.
It can be very effective. Of course, you still need to make sure you're applying enough of the major nutrients, N, P, K, magnesium, for phosphorus, because it gets locked up so easily.
Yeah.
Using split applications can help. Instead of putting it all on at once, you apply smaller amounts more frequently during the growing season. This gives the plants a better chance to grab it before the soil chemistry locks it away.
Right, feed them little and often. So it really sounds like there's no single silver bullet. It's a combination of approaches.
Precisely. That's the main message from the source material, really. Effective management, effective reclamation, getting good productivity requires integrating things.
Mhm.
You need the right irrigation, often the physical work like chiseling, plus those chemical amendments, and definitely the organic matter. It's about tackling all the limitations together. Okay, so let's just quickly wrap up the key points.
Huh.
Calcareous soils,
Mm.
defined by lots of calcium carbonate, very common in drier climates, especially vast areas in India. They present real hurdles for farming nutrient lockout. Physical barriers like crusting and hard pans.
Hmm.
But they can be managed. It takes a combination of irrigation, physically breaking up hard layers, using organic matter, sometimes chemical amendments, and smart fertilizer strategies like foliar feeding or split applications.
You've got it. That's a great summary. And, thinking about how widespread these soils are globally and considering the growing pressures, especially around water scarcity in many of these same regions, it really poses a question for you, the listener, to think about.
Oh,
Yeah, what other innovative techniques, maybe things beyond what we've discussed today, might be needed? What else could hold the key to really sustainable food production in these quite challenging environments?
that's a great question to leave folks with. How do we farm these soils sustainably long term, especially with climate change and water issues?
Exactly. It's complex, no easy answers. But understanding the soil itself, its fundamental nature, which hopefully we've helped clarify today, that's absolutely the first step.